Hello, everyone. Welcome back. Originally, I recorded one session on descriptive statistics, but it got a bit lengthy, so I decided to break it down into two shorter sessions. This is the second session on descriptive statistics. Uh, it'll be a bit shorter than the first session. Uh, if you remember, in the first session on descriptive statistics, we talked about measures of central tendency and variability. We talked about how to obtain those values in Jamovi, how to play with the data and get all those values we want to report in our study or for our project. And also we talked about, since we had different types of measures and values, then we also talked about when we should use each of them. So in this session, we're going to talk about a different concept, which is more about the shape of your distribution first, like whether your distribution of the data is normal or is suffering from skewness and kurtosis, and then how we can spot skewness and kurtosis if there is any in your data. And then in the second half of the presentation, I'll talk about the concept of standard scores and uh, why we need the standard scores, how to use them, and how to calculate them. Well, now that we have talked about measures of central tendency and variability, it's also good to talk about the distribution of your data and the different types of distributions in your data, and then how to proceed if you have any of these distributions. So the first concept I'd like to talk about is skewness, which is a measure of symmetry in your data. Uh, Generally speaking, we kind of I wish that our data has no skew. A data with no skew is a normally distributed data where its shape is like a bell. So it's very symmetrical. Uh, the mean, median, and mode, all of them stand in the midline, and the tails of the distribution are symmetrical. So this is usually called the normal distribution or Gaussian distribution or uh, bell-shaped distribution. There are different names for it. So if this is the case, you can easily report mean with a standard deviation and interquartile range for your distribution. However, this is not always the case, and most of the times the data is not normally distributed. So we have two different types of skewness, aside from once we have once we don't have a normal distribution, we have two different types of skewness. One is negative skew, and is one is positive skew. In the negative skew, we have a longer tail on the left side of the distribution. So in this case, the mean, the median, and the mode are not uh, placed at the same line. So we have first mean on the left side, and then we have median, and then we have mode, which is the most frequent observation in our data set. The mean is on the left side of the distribution because we have more outlier and extreme values on the left side of the distribution. That's why the left tail of the distribution is longer or fatter. So that drives the mean towards the left side. So if you have a distribution which is negatively skewed, then you could easily see that mean is not the most reliable central tendency measure to report. So you might think about reporting median instead of mean. Uh, on the other hand, we have a positive skewed data, which is completely the opposite of the negative skew, where the right-hand side tail is either uh, fatter or longer than the left-hand side one. So again, in the positive skewed data, the mean, the median, uh, and the mode are not at the same line. So again, if you have a positively skewed data, you need to think about what type of measure to report. Uh, so you want to report mean. If you want to report mean, is very sensitive to extreme values. So in the case of negatively skewed and positively skewed data, it might not be the right decision to do that. So you might want to report median, but at the same time, when it comes to the measures of variability, it's good to report standard deviation and interquartile range and range too, so that the readers could see the differences by themselves. Well, the second concept I'd like to talk about is called kurtosis. Uh, unlike a skewness, which was a measure of symmetry or asymmetry in the data set, kurtosis is a measure of pointiness in the data set. Um, in the sense that whether you have like very fat tails or you have thin tails in your data set compared with a normal distribution. So if you look at the figure here, the figure in the middle is a mesocurtic a distribution, which is kind of a normal distribution. These are like very strange names. I can't even pronounce them myself. But anyway, we don't want to memorize these names. We just want to know what the concepts are. So the one in the middle is called a normal distribution, where we don't have any serious kurtosis or skewness. But if you look at a distribution on the left, this is kind of a negative uh, a distribution with a negative kurtosis, because you could easily see that a distribution falls below the normal distribution, and it looks too flat. So, but on the other hand, we have a distribution on the right side, uh, which is very, very pointy. So that's a distribution with a positive kurtosis, where a lot of numbers are just clustered in the middle of the distribution. So again, just like skewness, uh, you need to look at your distribution and see whether your distribution is suffering from any uh, kurtosis or not. But usually the kurtosis of a normal distribution is 3. So a, a value above 3 or below 3 is an indication of positive kurtosis or negative kurtosis. And I also forgot to tell you that when it comes to skewness, the value is 2. So if a value is below 2 for skewness, then it's okay, we can proceed. But values above 2 for skewness are an indication of a serious level of skewness in our data. Um, so yeah, that you need to look at your data and see whether they're skewed or not, or whether they're suffering from kurtosis or not, and then you'll decide what the measure of central tendency or variability you're going to report based on this distribution. Well, now it's time to see how we could calculate skewness and kurtosis using Jamovi. So we have the data set already imported into Jamovi. We just need to go to Exploration tab again, click on Descriptives. You'll get the same uh, format here. Put picture naming latency into the variables box, and then just scroll down. So under the distribution title, you'll see skewness and kurtosis. Once you click on skewness and kurtosis, then you'll see some uh, figures here. So we have negative skewness in our data. You can see that by the a sign here, negative sign here. And at the same time, we have a negative kurtosis. You could see that by the sign here. So in order to calculate uh, whether we have a serious skewness or a kurtosis here, we always divide skewness by a standard error of a skewness. And if it's below 2, as I said, if it's below 2, it means that uh, we're safe to proceed and our distribution is not suffering from a serious level of skewness. So let's just calculate it here. So we have a skewness, which is 0.251 divided by 0.427, so which is 0.78, which is well below a um, 2, which means that our data set is not suffering from a serious level of skewness. You can do the same with kurtosis uh, and see um, whether it's suffering from any serious kurtosis or not. But yeah, that's the way we can measure skewness and kurtosis in our data set. Now imagine you have two groups in your project or in your sample, and you want to look at descriptive statistics in each of these groups. So uh, we're going to see how we can do it using Jamovi. So we go to exploration, descriptives again. So we'll put picture naming latency the variables list. And then we want to split it by, for example, fascia type, or you can do it by gender, treatment type. So basically, here you need to put a categorical variable or a nominal variable. A nominal or categorical variable has this shape here. So, um, and if you want any of these uh, descriptive statistics measures, you can basically click on them and then they will show it for you. So you have 15 people in the fluent group, 15 people in the non-fluent group, zero missing data. So the mean of the fluent uh, group is 1413, and the mean of the non-fluent group is 1486. So that means that the um, fluent version of aphasia, people with this type of aphasia, they could name the pictures faster than the non-fluent one. Again, I emphasize that the data here is artificial, it's just made, and none of the values or things you see here are real. And then you see the median, you see a standard deviation for each of the groups, you kind of see that the standard deviation for the non-fluent group is lower than the fluent group. It's not too much of a difference, but it still is lower. So that means that the uh, the people in the non-fluent group are uh, responding to the images or pictures or naming the images or pictures more similarly. And then we have IQR, we have basically anything you select here. Jamovi splits it across the group, and then we'll present the results here. So most of the times you have several groups in your project or in your research, and then you want to present the descriptive statistics across these groups. So that's the way we do that. So we can put the facial type out, and then it only calculates uh, uh, descriptive statistics uh, for picture naming latency regardless of the group. So let's put gender here again. So we'll put gender here again, and then you'll see that the result is kind of split across the levels of the gender. So you can play with the data like this and see like how it changes basically. Well, at the end of this session, I'll try to talk about standard scores and how we could use them in our research. So, if you could see from the name of this standard scores, basically they're standard scores. They're standard in the sense that uh, they enable us to compare like the performance of one participant with other participants in the same group, or if you kind of give two tests to the same participants, but the two tests are on different scales, a standard score such as Z-score enables you to compare the participant across to compare the performance of the participant across the two scales. So that's why they call it a standard score, because it kind of changes everything and puts it on a similar scale. So if you're comparing different participants, you're comparing different participants with the same standard score. So it's easy to interpret. Or if you're comparing someone across different tests, but these different tests have different scales, of course, if you report the raw data is misleading. So you need to convert the raw data into a standard score so that you can easily see your participant is doing good or bad in which of the tests. So I'll give you an example before we talk about it more. So imagine you scored 130, 130 in a standardized test. Scores of these tests were normally distributed. The population mean was 100 with a standard deviation of 15. So how did you perform in this test? This is like the answer to this question uh, is basically depends on how you calculate a standard score and how you interpret a standard score. All right. How we interpret a z-score when we convert our real score to z-score, and how we interpret that depends on a, very cool and nice property of the normal distribution. If we have a normal distribution, we know that 50% of the data falls below the mean and 50% of the data falls above the mean. So based on this property, we can kind of divide the whole normal distribution into different uh, parts. So this property of normal distribution kind of says that 68% point 2 percent of the whole data would fall between -1 to +1 standard deviation from the mean. The same property says that almost 96% of the data falls between -2 +2 standard deviation from the mean, and 99.7 falls within 3 standard deviation from the mean. So uh, a z-score and a standard deviation are very similar in the sense that instead of you can kind of uh, put z-score instead of a standard deviation in your interpretation, and then uh, you convert your raw score into z-score, and then you kind of look at this figure and you'll see where you stand in comparison with the rest of the population in the data set. For example, if your z-score is 1, that means that you are one standard deviation above the mean. So uh, that means that you performed better than 85, almost 84% of the whole population. Or if you like your z-score is -1, you only performed about like better than 15% of the population, and 85% performed better than you. Uh, so we have the uh, formula for z-score here, where you we have the score minus mean divided by standard deviation. So if we suppose that your score was 130 and the mean was 100 and the ST was 15, then it makes your Z score 2. And then if we go to the normal distribution, I and we and then we know that the standard deviation is 15, so two standard deviation above the mean would be 130, which is your score. And then if we look at the percentage in the shaded area, that tells us that you performed better than a 98% of the whole group of the rest of the group in the population or in your sample. So this is one use of a standard score. So you have a raw score, you turn that, convert it into a z-score, which is kind of influenced by the mean and the standard deviation. You put all of that into the equation, you get your z-score, and then you go to that property of normal distribution where we know like uh, we know the shaded area, we know like uh, how many percentages we have in each shaded area, and then you'll try to see where you stand in that normal distribution, and then you can compare your performance to the rest of the people. This is a very, very, very nice property which you need to be able to do if you're doing treatment or if you're doing a project. You people always ask you to compare uh, performance of somebody to other people, and then uh, that's how you can do it very easily. As I told you, another use of a standard score is to enable you to compare the performance of the same person across two different tests. And uh, that's also a very nice property. I'll give you an example first, and then we'll go through the example which makes it easier to understand this concept. So we have David here who took two tests, a Chinese speech perception test and an English speech perception test. So he got 80 in both of the scores. So if you look at the score, the scores are the same. So you might think that David performed equally well in both of the tests, but I told you that you always need to look at uh, the standard deviation and the variability of the data in order to be able to judge. So the mean is 60 and the standard deviation for the Chinese speech test is 10 and for the English speech test is 20. So we have more variability in the English speech perception test compared to the Chinese one. And then now uh, you know the formula. You need to subtract the raw score from the mean and divide it by the standard deviation, and you'll get the Z score uh, for for David for each of the tests. So for the Chinese speech perception test, the Z score would be 2, and for the English speech perception test, the Z score will be 1. Now let's look at where he stands, looking at the graphs. So if we look at David's performance in the Chinese speech perception test, his Z score is 2. So it means that uh, uh, he is placed 2 standard deviations above the mean, which is 80. We know that. And then we know that 2 standard deviations above the mean means that he performed better than 98% of the other people in the group. But if we look at the English speech perception test, the Z score is only 1. So that means that he only did better than 84% of the whole group. So this is very interesting. So the concept of a standard score is very cool and is very helpful in your research and in your career because it enables you to compare the same person with the rest of the people. It also enables you to compare people across uh, different tests with different scales. So you kind of easily see here that someone got the same score in 2 tests, 60, but that doesn't mean that he performed equally in those 2 tests. And you can easily see that here in this example. You can go through the example again and think about it, and then I'm sure that you can think about other examples in in the projects you're doing, or when you read papers or reports. Please think about the idea of a standard score, which is very, very helpful. This is the end of the second session on descriptive statistics. It was a short session. Uh, at the end of this session, I expect you to know what skewness and kurtosis are and how you can spot them in the data. I expect you to know how to calculate skewness and kurtosis in Jamovi once you have the data. I expect you to know what a standard score is and why we need standard scores. And finally, I expect you to know how to calculate the Z-score and how to interpret the Z-score depending on your context or research questions. Thank you for listening and see you next session. Bye bye.